relationship maintenance intention, the indirect effect is A11 times C61. And the total effect is A11 times C61 plus C11. If you have a diagram in front of you, if you label all the paths, then it will be easy. Just like here. So we have two dependent variables, BGI and RMI. Okay, so we have the indirect effect and the total effect. Finally, we estimate our model. Now, here you will see some new things here. On day one, when I said whenever we have indirect effects, we need to use bootstrapping. Here, this is the bootstrapping command. SE equals to bootstrap equals to 2000. Here, I also added one command. It's called mean structure equals to true. Actually, you may not need this in this particular example, but what that means is we also estimate the mean latent means. We also estimate the latent means. But what I want you to focus on is the line that I have highlighted. The line that I have highlighted is something that you don't need to change in any of the model. You just copy and paste this line. What this line is doing is in our computers, the new computers typically have more than one processor. Okay? So in most of your computers, I think you have 4 processors and typically has 8 threads. If you do not have this command and you ask bootstrapping to do it, it will only make use of one processor. So it will not fully use the resources, your computing resources. In this particular command that I have highlighted, it will use the maximum number of cores that you have in your computer. For example, if you have 8 cores, it will use 7 cores to do the bootstrapping. Basically, it will partition bootstrapping task into 7 parts, and it runs 7 parts, 7 bootstrapping, and then it will link the results together. So you can imagine it will be much faster than using 1 core to run 2000 times. So then we ask for the summary results, we ask for the fit measures, standardized results, and the R-square. And finally, we ask for the bootstrap confidence intervals. So for this example, the commands are on page 189, 190, and 191. In fact, I have saved the code in example A5. If you can find your file, example A5, then you will find all the codes in example A5. But before that, okay, we will work on this together. Before that, I'll open my R. The first thing you need to do is to change the working directory to where you have your data file. My data file is in the introductory SEM with R. Okay, I select this folder. The second thing that you need to do is to type library, Laverne. And sometimes, a lot of times, we will use SEM tools as well. So I type SEM tools. Now, let's work together. You can either copy and paste the 3 slides 189, 190, and 191, or in your file outcode example a5.txt. Uh, you will notice that it is a little bit slower than Monday because now we are working on the items. It is not too bad on my computer. Great, have you got your results?
Yes, but I got a warning message.
Warning. What
Yeah.
is the warning message?
Okay, I copy paste. Give me a second.
Yeah. Oh, interesting. Okay. Don't worry about that warning message. It says that among 2,000 bootstrap samples you have, it failed 241. It's not an issue, okay? As long as, most importantly, if you do see, oh, I got the same warning message. Okay. Do you notice that? Do you see that on my screen?
Yes.
I get the same warning message. It doesn't mean that your model is wrong. Okay, your model is not wrong. Okay, it's simply because some of the parameters are very close to the limit, and when we bootstrap, it goes beyond the limit. It doesn't matter. Okay, now first we will check the model fit. We have 224 degrees of freedom. Chi-square goes to 342. If you rely on chi-square, you will reject your model. It is bad. But if we look at the CFI, it is 0.98. RMSEA equals to 0.032 and SRMR equals to 0.038. That means the fit indices indicates that a model fits the data well. You get it? Okay, the first thing is to look at the model fit. It shows you the factor loadings and the standardized factor loadings. And it will show you all the regression, all the paths, the estimates, whether it is significant or not. Not many paths are significant. Okay, you can see that here, not many paths are significant. And the standardized path coefficients, standardized path coefficients. We also have the covariance. Now, in our model, although we didn't specify the covariance among the exogenous variables, it is by default, it estimates all the covariance among the exogenous variables. Do you remember we added the mean structure? When we add the mean structure, it will also estimate the intercepts. It will also estimate the intercepts for the items. Have the variance, the variables, and then the R square. Finally, we have our defined parameters. But for the defined parameters, do not look at the p-value because for our defined parameters, these are the indirect effects and the total effects. What we should do is to look at the confidence intervals. Of our defined parameters. At the bottom, you have the defined parameters and the confidence intervals. For example, you will notice that, I don't know whether you have the same number, on row 117, for the indirect effect from BE through RE to BGI, if the estimate is 0.06, if you look at the p-value, it is not significant, it is 0.059. But if you look at the confidence interval, 95% confidence interval, it is significant because both have a positive value. That means 0 for outside. You get it? So we should report the 95% confidence interval for the indirect effect instead of the p-value. Your confidence interval is not a border. What confidence interval do you have here? Oh, it's your unlucky day. But is your estimate the same? 0.06. Good. Okay. So you will notice that the estimates are the same, but the confidence intervals are not. Okay. Why? The reason is we bootstrap. We use bootstrapping. Okay. And bootstrapping here becomes 2,000 times is not enough. This is not stable. Okay. So maybe since we have time, let's do it one more time. You don't need to define your model again, okay? But here, instead of 2,000, let's change that to 5,000 to see if we get the same results, okay? Do you know what I'm doing? On this slide, page 191, if you change the 2,000 to 5,000, let's copy and paste this to your R to run again. It will take a little bit longer because now we are running 5,000 times to see if the results, if we have the same results. You got the results. Mine is a little bit different than before, but I still get a significant result. Juliet, what do you have a similar confidence interval now? Hello? Still running. Good. Okay. So I'm showing you that my computer is faster. My computer is much faster than others because I have 16 cores and 128 gigabyte RAM. Most of your computers have about 4 to 8 cores, okay? But my computer has 16 cores. So I'll wait for you. Yes. Okay, it's closer.
Yeah, got the question. On line 123.
Wait. Okay, let me finish this first. Okay, to it. If you find your results are just mirrors, just like before, Okay, when you run 2,000 times, you have minus 0.01. Okay, it may be just your unlucky day. What I would suggest you to do is to increase the number of bootstrap samples and run it again. Have I made myself clear to everybody? Okay, so yeah, Kate's got the similar answers as I have. Okay, so although the upper limit is a little bit different, maybe in the future I should suggest people to use 5,000 times. Okay, but you need to buy a new computer. Maxwell, you have a question.
Yes, the same token, 123, and then it seemed to be insignificant, but the confidence interval is so narrow. What's your
Yes.
suggestion?
Well, there's nothing you can do because it simply means that it has a very small standard error. It has a very small standard error. The reason why the confidence interval is that narrow, do you notice that the estimate is 0?
Yeah,
123.
Yep.
It is not 0. It may be the 4th decimal point, 5th decimal point. Right? So you will see it is very narrow, but it is still not significant because the effect is very small. The indirect effect is very small. You get it?
Thank you.
Good. Okay. One more thing. Now you know how to run bootstrapping. One more thing. Do you notice that now our model, before we run bootstrapping, we have estimator equals to MLR. But now we don't have this estimator equals to MLR here. The reason is the objective of using estimator equals to MLR is to adjust the standard errors. But when you use bootstrapping, we do not rely on the calculation of standard errors. We rely on the bootstrap sample to find out our standard errors. Therefore, making adjustment is meaningless. If you make adjustments, we are not going to use those standard errors anyway, because the standard errors are from Bootstrap. That's why we do not use estimator equals to MLR in bootstrapping. Do you get my point? We do not use estimator equals to MLR in bootstrapping because MLR tries to adjust the standard errors. But whenever you use bootstrapping, you generate the standard errors, which is not normally distributed by using bootstrapping. Therefore, you don't see estimator equals to MLR. If you put down estimator equals to MLR here, you will get an error message because it is conflicting. Okay? So Sinqua yesterday asked about the width. When I have the confidence interval, ask for the confidence interval, I usually put width equals to 180 or 200 to make sure that I have everything on one line. First, we look at the fit indices. Make sure that your model fits the data well. And then we can look at the parameters. Here are the factor loadings, standardized factor loadings, the regression coefficients, standardized regression coefficients, whether it is significant or not. And then the intercepts and the residual variance and the R square. And also, finally, we have the confidence interval. Tell you what, I think Laverne used a different simulator to do the random sampling comparing with M+. In M+, if you use 2,000 times for bootstrapping, it should be pretty stable. But now I noticed that in Laverne, 2000 times is not stable enough. We get different answers. So maybe in the future, if we use Laverne, we should increase the number of bootstrapping to 5,000. Because they have a different way to generate the random sample. This is the full model. Do you have any questions about the full model?
Just for the purpose of clarification, before we run the full model, we should follow your suggestion yesterday to utilize the measure Q to test the measurement reliability and validity, right?
Correct.
Okay.
Before you test any model, you need to use measure Q to state that you have good reliability, convergence, and discriminant validity. To demonstrate it, you are measuring your variables well before you can test your hypothesis. Okay?
Thank you.
Good. Any questions on the full model? So if you go back to the syntax, it's nothing more than combining a measurement model and the path model. If you have indirect effects, you just define your indirect effects and total effects. So all the other steps are the same. You run, because you have indirect effects, you use bootstrapping, and then you ask for the confidence interval. Any questions? Well, now I finished with the full model. Before we move on to talk about some minor issues, or well, I won't say they are minor, but some different issues not relating to the model about SCM. Why don't we take a 10 minutes break, and then we will come back to talk about missing values, how to select variables, etc. Okay? And 15. Hey, are you back?
Yes.
Okay, now, Xinhua asked a question about here, bootstrapping. I'm on slide 191, okay? She asked this bootstrapping, whether it is percentile bootstrapping or BC bootstrapping. Okay? In fact, for bootstrapping, when you run bootstrapping, it doesn't matter, there's no distinctions between percentile bootstrapping or bias corrected bootstrapping. The bootstrapping procedure is the same. The only difference is here. The only difference is when you ask for the parameter estimates, the bootstrapping confidence interval type is whether it is percentile or BCA.simple. Let me see if I can find. Parameter estimates. This is the Laverne manual. To estimates. BCA is for the bias corrected. I think it is the PERC percentile. If you want the percentile method, you can put PEC. Let me see if it is correct. PERC. Oh, I see. Then you get the percentile method. So have I answered your questions, Xinhua? The bootstrapping procedure is just bootstrapping 5,000 times and it estimates all the parameters, but the way how you calculate the confidence interval, how you request the confidence intervals, depends on what confidence interval you request. Here, I can request percentile or bias corrected. So the next thing, there are some minor stuff that we want to do manipulating your data files, okay? First, how to handle the data frame. So first, we read our CSV file into a data frame. Suppose your data frame name is DF, okay? How can we select observations, which is a subset? Okay? There are two ways you can do it. Okay, it is clearer if you work it on your Excel file. You just copy your Excel file, CSV file, into a different file name, and then you select from there. But of course, you can also do it in R. The first one is supposedly you have a variable gender. You have both male and female, but now you only want to analyze the male group. So we create a new data frame called DF2. And we use the subset. DF is our original data frame. And we want to have a column, a variable named gender. We select only the M. Again, here, you will notice that for R, the equal is not one equal sign, but two equal signs. In this particular case, we will analyze only the male subjects. If you have more than one choices, for example, it is a US data set, okay, we have the state, if we want to analyze both California and Washington, D.C. Okay, so we have in the state, we want to select all those observations which are in California and DC, then we can use percentage in percent, this command, percent in percent. And then we have CA, comma, DC in quotation. So we select both CA and DC in our new data set. If you don't want to bother about this, I think it will be a lot easier if you use your Excel file to select your subset of observations. You can have more than one condition. Here, the stroke is typically or. So either gender equals to M or state equals to Philadelphia. You can also use the and. That means we want the gender equals to M and state in California and New York. This is how we select the subsets. There's a link at the bottom. Oh, I need to open the door for my cat. Okay, sorry, my cat just woke up and I need to open the door for him. Maxwell, you have a question?
Yes, and here you think that we declare data frame is DF, and then is there a command in R that we clarify, hey, the data frame refer to this CSV or refer to this particular Excel file?
So what you need to do is, in fact, like what we did all the time, you need to read your data file, CSV file, into a data frame first. So in that particular example, we put DF here.
Thank you, very clear. Thank you.
Okay. Any questions? No? Okay. Well, I want to add one more slide that I have not included here. I want to talk about one more topic, which is more than just selecting the observations. So here you can, this slide, you can select the observations, right? Okay. I don't, why I always have to full screen. Okay. Here. Okay. Now, let me show you one more thing. Recoding. A lot of times, we have negatively worded items and positively worded items. Okay, we have negatively worded items and positively worded items. We need to recode those items, the negatively worded items, such that all the items are in the same direction. Do you understand what I'm talking about? Supposedly, we have x1, x2, x3, and x4. Supposedly, they are in 5-point scales, 1 to 5. 1 to 5. And supposedly, x2 is negatively worded. Before you run your analysis, you need to make sure that x1, x2, x3, and x4 are in the same direction. So we need to create something, we need to recode x2. Okay, Do you know what I'm trying to show you? Okay. Now, how can we recode X2? First, you need to read your Thank you, Chenya. You're doing the Chinese translation. Okay. So first, we need to read our Excel CSV file into a data frame. Then what we can do, like here, now our data frame is, I put it back, example.a5. Let me see if I can make it bigger here. Okay. If we want to recode X2, first we read our CSV file as a data frame, example.a5. Then we recode here. We create a new variable in the data frame called nx2. Called nx2. How we can do this is data frame name, a $, and then nx2. So our new variable is called nx2. When you recode, reverse coding a variable. If it is 1 to 5, you use 6 minus your original variable. Starting from here, 6 minus my original variable is example.a5. Now, because it is a matrix in your data frame, we put a square bracket, a comma, means that all the rows, and then the column x2. So we are recoding all the observations from x2 to nx2 by using this equation, 6 minus x2. So recoding x2 is 6 minus x2. This is how we do it in R. We create a new variable, nx2, which is 6 minus x2. We first read the CSV file into a data frame, and then we create a new variable in the data frame example.a5. So example.a5 $nx2, 6 minus example.a5 square bracket, comma, and then quotation your variable name x2. This is how you can recode your variable in your data frame. Of course, you can also do it in your Excel file. You can create a new column in your Excel file and use 6 minus your column of x2. Tuyat asked whether I am showing how to recode the reverse items. Yes, the answer is yes. I'm showing how to code the reverse items. Do you have any questions about this? One more thing. For most of our items, we use 1 to 5 or 1 to 7. But sometimes we have tenure and age. Age may be much larger number, okay? So it probably between 20 and 60, right? Okay. in some SEM analysis, the variance of age will be much larger than the variance of your items. Do you get my point? Do you know what I'm talking about? The variance of age will be much larger than the variance of the items. In that particular case, some SEM models depend on your models. It may give you an error message because the variance deviates by too much. So what you may want to do is to recode your age variable. I call this NH here. Sample dot A5 age divide by 10. I divide all the age by 10. Okay, it will not affect. We are just rescaling the age variable. I don't know why they like to auto change my uppercase and lowercase. Okay, so we are reducing the scale of age, for example, from 20 to 60. Now it becomes from 2 to 6, which is much closer to the scales of the other items, such that you won't have this problem that one variable has substantially larger variance than the other variables. Sometimes it may create a problem and you won't be able to estimate your model. So a lot of times for age and tenure, I will divide it by 10, such that it will have a closer range with the other items. Have I made myself clear? Okay, create a new variable, NX2, rather than replacing. Yes, correct. Okay, Chinya, Professor Hu highlighted that we are creating a new variable, NX2, instead of replacing the X2. We don't want to replace X2. We use, because we always keep the original data. So you will want to create a new variable. This is not Laverne. Eugene asked the question, okay, where we put this? In fact, you put this before your model. You do all the recoding before your model. It is not in Laverne. The first step is to read your data frame. The second step is to specify your model, right? Okay, so you put it in between here. You put all the recoding here, such that you create a new data frame with the new variables. But then you need to remember your recoded variable now, it is no longer X2, but NX2. Okay. Well, Maxwell said that, okay, should we instruct R to save the new data set? Yes. Okay. But if you bother this, I will just do the recoding in your Excel file. Do you get my point, Maxwell? Yeah. Okay. And let me see. I should have an example to show you how to. Let me stop sharing now and I'll find the command for you to save the file. Okay, I just find the command for saving